Okay. All right. Yeah, so I'll get started. So I'm Aurel. This has been a joint work with Jonas, Hansen, Alexander Summers, and Peter Müller, and I'll be talking about specifying and verifying iterators in Rust. Before I get started, I want to sort of clarify the scope. This is about iterators in Rust, which are many things, but are not, for example, iterators in C++. In C++, you have similar concepts called ranges and views recently, or in Java, you have these streams. So that's the kind of feature that I'm talking about. So to begin with, I want to make this kind of point that iterators in Rust hide a lot of complexity, which is both good because your code looks nice, it's quite maintainable, it's easy to read, but of course there's a kind of cost to this, right? The compiler has to do something about this, and also to specify and verify these things, we'll find some challenges there. So as a very, very quick intro to iterators, let's construct an iterator chain. So here we start with a vector of, let's say, integers. We call this iter method to get an iterator. We call map. So here we will apply this operation of adding 1 to each element in the stream. Just note this is the syntax for closures in Rust. And to make it more interesting, we'll also make the closure have a side effect. So in this case, the closure will mutably capture this sum variable and update it so we have a sort of cumulative sum of all the elements this map has seen thus far. And so the result of map is yet another type that implements iterator, so we can apply more operations such as filtering out only the even numbers. And finally, filter gives us yet another iterator, so we can collect this into, say, a vector. So this is what we call an iterator chain. It's simple, but if you look under the hood, the compiler has to think about a lot of things. So if you spell out the actual full types that are going on here, they get kind of gnarly because sort of everything has to be tracked really precisely by the Rust compiler. So looking concretely at this filter type, we see that the final type of this filter iterator contains in it as a type parameter the map iterator, which contains in it the iterator over slices that we got to. This is good because it allows the compiler to not have to box values, which in Java streams you have this int stream type to avoid this kind of thing. It means that the compiler, because it also keeps track of precisely which closure type was actually passed, can generate code which is as optimal as if you wrote this loop yourself. And of course, in Rust specifically, closures, especially the first one, captured some variables, so we need to keep track of lifetimes. But then let's look at what we can do when actually verifying this code and what some of the challenges might be. So the first very general one is how to even specify iterator behavior at all. And then as sort of sub-problems, I'll focus on how to specify iterators which are parametric in a closure, and also ones which are parametric in a previous iterator in a chain. So this is all done in the deductive verifier called Prusty that we work on. It is a deductive verifier, which means when you verify some code, you get pretty strong guarantees about what just happens. And the cost there is that you are expected to provide some specifications. So namely, we provide, as users of Prusty, preconditions and postconditions on methods and things like loop invariants. Another thing that Prusty is, it is a modular verifier, and I mean method modular and sort of type modular. So we would like to express the specifications once and for all. We want to have the specification for the iterator trait and for iterator implementations. It shouldn't be the case that for every single iterator chain that we build, we need a completely new specification. So let's start with this first problem of just specifying iterator behavior at all. So here we have a counter, which I'm not showing the implementation of the iterator trait, but you can see its behavior very simply. It has one number which keeps incrementing and one upper limit. And so as we repeatedly call this next method, we get the values 1, 2, 3, and then it tells us, okay, I'm done. And this next method is the one crucial part of an iterator implementation. It's the one required method. So how do we specify this? So our answer to this is to provide these specification ingredients, and I'll explain each of them now in turn. So here we can see sort of the state flow of this iterator, as we call this next method. And so the things that we focus on are, firstly, when does the iteration actually stop, if ever? So for this, we define some kind of stopping condition. And here we choose to define it as the function from the state of the counter, which tells us whether it should stop. And in this case, the condition is whether the numbers are equal. So then, ignoring this part, when it's an iterator, what it matters to us is, of course, the sequence of values it actually produces. So we talk about this as this produced sequence of values. And note this is sequence as in something that is only available to the verifier and not an actual collection type. And also focusing at the states themselves, ignoring the fact that we're actually calling this next method. Each step in this iteration, we can find some kind of relationship between successive states. So we define this one-step predicate called step, which relates a previous state to a current state. And we can see that with each step we increment the first number by 1, and crucially that the second number stays the same. But there's also one more situation which we need to account for. And so, for example, if we have this kind of mutate method which accepts an iterator and it accepts it by a mutable reference, well, we don't know what the mutate method might do. And in particular, it might call the next method of the iterator some number of times. It might be 0, it might be more. In this case, we just don't have any specifications for mutate, so what can we actually assume? And so for this, we want some kind of predicate which we call leads to, or an n-step predicate that still holds after arbitrarily many calls to the next method. And so in this case, what we can find is that no matter what the value of the counter is after the call, it must have monotonically increased. It cannot have decreased. And the limit itself is also not changing. So cool. We have defined these ingredients for our basic counter iterator. More generally, they will have this kind of signature for just iterators. So this was our first problem, and our solution to this was to define these 4 specification functions. So then let's get to a more complex case, which is the closure parameter case. So here I will define yet another iterator, call it repeat, which is generic in this F type, and it says this iterator contains a closure which will give out some values and accepts no parameters. As an example, we'll construct essentially the same thing as before, a counter, just this time it does no stopping condition, and its behavior is like before. So the question here is, well, how can we define these ingredients, these predicates and the stopping condition, when what we're talking about is a closure contained within this repeat iterator? And in particular, in the example I showed, it seems like this is the sort of flow of states that we have. That we have this repeat iterator which somehow calls the method, and on the side there's this variable x which keeps increasing, but it's hard to find the connection. But of course, this is where we realize we are actually in Rust. And so there are some guarantees that Rust ownership gives us. So namely, repeat owns this closure for the duration of its lifetime, and in turn, the closure owns or mutably borrows or captures, whatever you want to say, this x variable. And so actually, the way we can represent these states is maybe more accurately represented this way, where the repeat iterator contains this x variable for the duration of its iteration. And so more generally, this repeat iterator will contain some function states. So now the question is how to specify the repeat iterator. And so here we will turn to some of our previous work in closure verification. So there is also a similar concept for sort of a one-step predicate of a closure. We express this in specifications with a call description. So this is the general syntax, and essentially this is an assertion which states that a call has happened, that a call to this specific method happened with some parameters, which in this case there were none, taking the closure state from one state to another, and optionally, not in this case, maybe there was some result. This is vastly simplified, but this is sufficient for this talk. So this is a useful assertion, and it just talks about calls to functions. So in the case of the repeat iterator, we can pretty directly use it as, or reuse it as the one-step predicate of the iterator. We're saying that the one step of the repeat iterator is the call description of this method f. And similarly, if we pass the repeat iterator to this mutate method, well, we also want some similar notion of an n-step predicate for closures, which we call a history invariant, which you can also define for the closure. So cool. We have used our closure specifications to define the behavior of a repeat iterator. And now the question might be, did we actually specify anything at all? Because it seemed rather abstract. So here I want to bring up again the point that Prousty is meant to be a modular verifier. So in particular, we only want one specification for this type. And so although at the point where we specified repeat, we defined this rather abstract call description to be its step predicate, what this actually allows us to do is that at a particular call site where we know the definition of the closure, where we know its specification and history invariant, we can instantiate the specification, and basically the step predicate of repeat becomes this one, where we can talk about the x variable actually being updated. And what is important is that this step should be done by the tool, or in other words, our specifications should allow the tool to perform this instantiation automatically rather than have the user write new specifications for each iterator chain. Yeah, so just to summarize, for this part of the problem, we used call descriptions and history invariants. So moving on to yet another slightly more complicated situation, we have the slightly simplified version of the map iterator from the standard library. So this is now what's called in Rust terminology an iterator adapter, in that it takes an existing iterator, the previous iterator in the chain, and then adapts its results to become, yet again, an iterator. So reusing the repeat iterator as the previous link in the chain, we can construct map manually by just passing the iterator as a parameter and now applying this double enclosure, for example. The behavior is unsurprising. We can once again think of the state of map as being composed of what it actually contains, which is the state of the iterator that's previous in the chain and the state of the closure that it's being used with. So now let's focus on one application of this next method. So what the map implementation will actually do is it will query the previous iterator in the chain. So it will call the next method. And here we assume that it gives us some results still, so we'll call it some v. And this v value will then be used to call the closure contained in the map. So this is this call mute. So to define the step predicate for map, for the time being, we will existentially quantify over this v. I'll talk about this in a second. we'll say that v itself was passed to this call mute representing the function call, taking the, in this case, f0 state to f1, and that the some v value itself came from a call to iterator next of this I0 state moving to the state I1. So this is a kind of generalization of the call descriptions that we had previously, in that it's not only describing closure calls, it's describing arbitrary method calls with slightly more interesting things we can do about the pre-state and post-state. Yeah. What we're not showing is that, of course, the previous iterator can return none. This is just some kind of match that we need in the predicate. And that in the actual implementation, we also avoid this existential quantification with something called ghost sequences, just for better automation. More details in the paper. So our problem in the third case was how to specify iterators with iterator parameters, and for this we generalized this previous concept of call descriptions to talk about more general APIs. And as a final point, I want to bring up something which I title incremental verification, I guess. If you imagine applying this methodology to a large code base, you might face some issues if this is implemented sort of naively. So in particular with Prusty, we believe that it's important that you can sort of gradually buy into verification and stronger guarantees by sort of gradually providing stronger specifications, for example. And if we just made these iterator methodology ingredients part of the iterator trait, well, this would be a bit of a problem, because you can implement your own iterators, and now suddenly your code base doesn't verify because you don't have definitions for these ingredients. And so the problem is basically how to add the specifications to the iterator trait without forcing the code base to replace all usages of iterator with our own trait or something like this. So first of all, there is one problem here that's already solved, which is that there is a type defined in a different crate, in this case the standard library, and it has some methods, and we want to attach specifications to them. This is simply called an extern spec. So what we could do in Prusty is define an extern spec for an iterator, add some preconditions and some postconditions. Yeah, but if we actually start to try to use this methodology, well, the problem is obvious. Like, I start writing one of these postconditions that say the iterator will not return none unless it has finished its iteration, but I cannot call done because this is not a method of iterator. So how do we actually load our functions into here? So the solution we go for is we define all these methods in a different trait, make it a subtrait of iterator, so anything that it implements this iterator spec must also implement iterator. And then we use our novel concept of type-dependent contracts. So this is a contract which only applies if an additional trait bound is satisfied. So namely, if the current implementation of iterator also implements iterator spec, then this is the contract, and you get sort of a stronger contract that must be a behavioral subtype of it. And then to actually provide specifications for all these standard library iterators, these turn into concrete implementations of iterator spec of our own specification extension trait. Yeah, and so just to re-summarize, I guess, our problem was how to integrate with realistic code bases. We applied this type-dependent contracts idea. We have found, since working on iterators, that this idea is rather useful in other situations. In particular, there are many marker traits in the Rust standard library where this kind of thing naturally fits. And the particular design we chose, where the trait bound that it needs to be satisfied is written in the extern spec of the trait being extended, also fits in very nicely with the idea of trait coherence in Rust, where essentially this is a system which ensures that for any trait method call, there's only ever one definition. So we want a very similar property, which is that for any trait method call, there is only ever one contract. I will briefly discuss some related work. There was an old challenge in 2006 about specifying iterators. One of the solutions was this reasoning about iterators with separation logic, which was a rather manual approach. In 2018, there was a much nicer, or more automated rather, approach, which has sort of similar ingredients to what I described, but it's not general enough to describe, for example, composition of iterators, or to talk about the state of the iterator as it evolves. And finally, very recently, there was a talk you might have seen by Xavier, where where Rust iterators are also specified and verified in the Crusoe system. This was work developed in parallel with this, just to be clear, but they do not address this code-based integration problem. Some future directions, I suppose. This idea of these type-dependent contracts is very similar to what trait specialization might do in Rust eventually, when it's sort of more publicly available and more stabilized. So it could be that type-dependent contracts can be eventually replaced with this proper feature. You might have noticed that this n-step predicate leads to feels very similar to a type invariant for an iterator, and indeed it is. We designed this methodology for verifiers which do not necessarily have such a feature. And finally, itermute, which is an iterator which allows you to mutate, for example, the elements of a vector as you iterate it, is something that we believe our methodology should support, but the Prusty underlying tool doesn't at the moment, so oh well. And yeah, this is it. Thank you.
Great. Thanks for an interesting talk. And once again, are there any questions? Yes.
Hi. Thanks for an interesting talk. At one point you said, so here's the existential quantifier, and I'll get back to that. So I'm a bit confused about you're writing steps 2 as a Rust function, but you're using it in the specification. So should I understand that as like a pure thing, which is not actually Rust code that will be run, but it's just to help verification? And then the second question is, how do you do this with this existential quantifier? How does that?
Yeah. So all the ingredients of the methodology that are presented in the iterator spec trait are marked pure in Prusty, which means they should be side effect free, deterministic, the usual stuff. But they're still Rust code. Like you could run them, but they're also suitable for use in specifications. For the existential quantifier, so the solution we have is basically called ghost sequences. It maintains a, for something like map, you maintain a sequence of all the states of the closures and the previous iterator. And so the value that you actually obtain from the call to next of the previous iterator is determined from this existing state. At a concrete instantiation, at a concrete call site, these sequences sort of become spelled out, if you want, and allow the verifier to do this kind of reasoning without actually having to prove existential witnesses.
Is this n times steps 2 method just always the reflexive transitive closure of the one-step thing, or are there useful instances where it's more general?
Yeah, we describe it as the transitive closure. I think it's generally what you want. In general, we asked the user to actually provide this because it's the same problem as inferring an invariant of a loop. So, I mean, you can have a less specific, less precise invariant, of course, and maybe that's sufficient for some proofs that you do.
All right, thank you. Thanks for the talk.
Okay, then let's thank the speaker again.